Assalamu alaikum ji. This is Dr. Numan Islam, and we are learning the course of numerical methods with the code MATH351. This is our fourth lecture, and in this lecture, we will be just doing the follow up from the previous lecture. That was the bisection method. So, just a review of the last week, what we have done in the last week. After the introduction of the course, we started with the mathematical preliminaries. So, in the mathematical preliminaries, we started with the first thing, which is how to round off the real numbers. And after that, we started with the Taylor series. What is the Taylor series and how to approximate the functions using the Taylor series. While doing this, we learn about the round of errors, absolute errors, relative errors, truncation errors, percentage errors. We just revisit those ideas. And in the last lecture of the last week, we started the intermediate value theorem. So the intermediate value theorem gives the foundation actually about um, the finding or about the identifying a solution of function in certain portion of a real line. So just to revisit what was the actually consequences of the intermediate value theorem that we are using. Um, just to revisit. So for example, if we have any function which is continuous on some interval a to b, okay, and second thing is the function values at the endpoints are different in signs, okay. Uh, then if these two conditions hold, then there exists at least one point p in this interval where function becomes 0. And we have seen it in a very comprehensive way that what are the possible options we can have if f of a, f of b is less than 0. So we got odd number of roots, okay. And if f of a, f of b is greater than 0, then we can have no solution. That is also an option, and we can also have even number of roots, okay. So out of the two, we have developed that this option will be a wise option in terms of going towards finding a solution in some interval, okay. So graphically speaking, this was the um, uh, view. If we try to understand through graphically, if this is a height f of a and this is a height f of b, then a function has to travel from this height to this height, and it is a continuous function, so we can't have any breaks. So it has to cross the x-axis, and this is a point which belongs to this interval and where the function is becoming 0, and we are interested in finding this point, okay. So we just seen in the last lecture that when these two conditions hold, then we can identify a point in certain interval where the function is giving us a 0 height. It means if we are trying to solve any equation, if that equation is passing through the x-axis, so that will be a point where we got a solution. We got a solution of an equation. Okay, we started with the example which was x minus cos x is equals to 0 on the unit interval. Okay, so we have seen in the last lecture that there are a solution that we try to find up to certain decimal places. Okay, we did some exercise in the last lecture that its solution will be a point which is 0.7391. Okay, so if you can go back to this actually table, you'll see a solution is going towards that point 0.739. Okay, so we try to go towards a solution by following a certain procedure. In this lecture, we will try to formalize that procedure that we're doing in the last lecture. Okay, so it's just a revisit of what we were doing in the last week and where we stand. Now we will try to develop a pseudocode or our algorithm of the bisection method, and we will if first we will try to develop some preliminaries that we required, actually some points to formalize this method. So I'll be going through those things, and then I will be trying to develop a pseudocode that we're going to implement on MATLAB. Okay, ultimately. Okay, so let's try just first to revisit what was the number of steps actually involved while we're trying to following the bisection method. Okay, so hopefully you remember. If I just take one example of this example, we just revisit the problem. So here we have, if we need to find a solution of this equation, and let's say the accuracy is 10 raised power minus 3. So this is the accuracy that we wanted. We know it is a very important condition to put, because whenever we have an irrational solution, we will not be able to find exactly. So if we are giving a solution approximately, then that approximation must be up to certain decimal places. So this actually information is required, that how much accuracy you want in terms of a solution of this equation. Okay, so let's say I'll just go through the procedure that we followed in the last lecture. So we have this equation, generally speaking, and we have an interval a to b, and let's say the accuracy that is we wish to find, let me call a word, it's also called a tolerance. So there is a word for the accuracy, it's also called a tolerance. How much tolerance you want to achieve. Okay, the same as the accuracy. So I'm just using a word TOL for the tolerance. Okay, this tolerance we need to achieve. So generally speaking, these are the terminologies, and what we do is actually, this was the first step. We take a half of the interval. Okay, when we take a half of the interval, then we check, is it a solution or not. How we check is it a solution? We plug this central point into the equation and try to see, is this a solution or not. And how we check it? Is it near 0 or not? Okay, so if I just go back to the calculation we did in the last lecture of this problem, so we have a middle point 0 plus 1 divided by 2. So this is 0.5, and at 0.5, so the answer was minus 0.3776. Okay, this was the answer that we got in the last lecture. So now this is not near to 0. This is not near to 0. Okay, near to 0 by what amount? Okay, that is what we wanted. It should be, when we plug the value of p into the function, it should look like this at least. So this is 0.001. Okay, so there is a 0 up to 2 decimal places at least. Okay, so if I get a number p at which the answer looks like this, then I'll say, okay, I'm getting near to the 0 that I wanted, near to the tolerance that I wanted. Okay, so obviously this is not the number that is 0 up to the given accuracy. So we'll try to see, okay, the next step of the algorithm was that if, for example, we have an interval a and b, and this is a central point, and if it is not a solution, then we have to discard one of the subintervals, or in other words, we have to choose one of the intervals, subintervals. Okay, so particularly in this question, at point a we got a sign of the function, so we need a sign of f, which, what is f of x in this case? X minus cos x. Okay, and when I plug 0 in this equation I got a negative value. Okay, it is 0 minus cos 0, it is minus 1. Okay, and if I plug a value b which is 1, it was 0.4. Okay, approximately 0.45. Okay, so it is a positive value. Okay, it means 1 minus cos 1. Remember, you have to use a radian mode of your calculator. Don't use a degree mode. Okay, by default we have calculators in degree modes. Try to convert them into radians. Okay, so if this point, which is a central point, it is not a solution, we need to see what is the sign at this value. It is a negative sign. Okay, so now we have subinterval I1, we have subinterval I2. So our solution lies in which subinterval? In I2. A better way to say is we are sure that the solution lies in I2. Okay, we are sure that the solution lies in I2. So if the solution lies in I2, so then I will move this A to this position. In other words, I just need this subinterval. So A will be moved to this position. So A will have 0.5 and B will have a value 1. Okay. So this is the point at which we are not. At this moment, we are at this stage. Okay. Now, what we have to do is, so let me just write this particular setting over here. Okay. So if f of a times f of p is less than 0, I need your comments on this. For example, the function value of a, so try to just understand through this example. If f of a and f of p, okay, so let me write over here just to understand, just to align with this particular example. If f of b times f of p, so what is f of b? F of b is positive here, and what is f of p? It is negative here. Okay, so if the product is negative, which variable has to move? A has to move. Okay, if f of this is the sign of f at b, and this is the sign of f at p. So if the signs are different at these 2 points, then the solution lies between these 2 points. So if the solution lies between these 2 points, then I don't need this subinterval. If I don't need this subinterval, which variable has to move? A has to move at this position. Okay, so A has to move at this position. So what I'm going to write over here, if f of b into f of p is less than 0, it means solution lies between b and p. So then A is going to get what value? P. A is going to get the value. Otherwise, what is otherwise? Otherwise means, so this is the point A, this is the point B, this is the point P. And for example, this, the sign of f is negative at A, it is positive at B, so solution lies between the two. When we take a middle point, that is not the answer up to the accuracy we wanted. So, but then we try to see what is the sign. Okay. So, if f of b, f of p is less than 0, then we have moved A. What we meant by otherwise? Otherwise means it should be greater than 0. That is the otherwise now. Else means otherwise. Otherwise means the product of these two is positive. Okay. So what would be the sign over here if that is positive? Here we will have a, because one of the sign is positive and the product is positive, so this must be positive. So I'm talking at this point, not in this example, I'm talking generally. Okay. So if the solution does not lie between these 2 points, obviously the sign over here will be positive. Okay. So if that is the case, then we have to move which variable? we have to move this b at this position. So either a will move towards the point P, or B will move towards the point P. And this statement, if we write, for example, like this, if f of B times f of P is less than 0, it shows that the solution lies between B and P. So we have to move A. Otherwise, we have to move B. You can see a scenario. This is a scenario where we're trying to move this point B because we don't need this subinterval. Okay? And we actually need this subinterval. So B is equals to B. Okay. So I'm just giving you a scenario again. So try to see a case one. So let me just deal a case one. Okay. So for example, this is the scenario point A, point B, and this is the central point. Okay. And let's see, this is sine of the function. Okay. For example, we're just discussing it. So at point A, function has a negative sign. At point B, function has a positive sign. Okay. And at point P, which is a central point, and at that point function does not give a solution up to the accuracy we wanted, the sign is, let's say, negative. We have a negative sign. So if this is the case, which is the case I've just written, for example, if f of b into f of p is less than 0, it means the sign at p, which is negative, and the sign at b, which is positive, the product of these two is negative. So it means solution lies in this subinterval. So I have to move a to this position. So if f of b times f of p less than 0, then move a towards the point b. And what is the case 2? What is the other option we have? If I just draw the same interval, which is a and point p, so at a we have a negative sign, at b we have a positive sign of the function f, and let's say at the central point we got a positive sign. Okay, so now the solution lies, sorry, it's b. Now the solution lies over where? In this subinterval. So it means I have to move this b to this position. Okay, so if we start a problem at a stage where the solution lies between in certain interval a and b, and then we did a midpoint, and midpoint is not a solution, then we have to decide either we have to move a or we have to move b to a central position. Okay, so this is the condition that will tell you if f of b times f of p, it means function at b and function at p have different signs. If they have different signs, it means the solution lies between them. It means we have to move the value a towards b. Otherwise, we have to move b, because that is the only option we have. Either we have to move a or we have to move b. And we have determined that if this condition holds, we have to move a. So it means otherwise we have to move b. Okay. So let me just okay. Okay, the process was, just to write, process was, first you have a function and an interval, and you need to find a solution up to certain decimal places. Okay, that is called an accuracy. Other word we use is tolerance. Okay, step number 1 is find the center of the interval. Okay, and step number 2 is check. What check we have to do? is P a solution up to the tolerance we wanted? Is it a solution or not? So we have to check. Okay, so we have to check this thing. So how we going to check this criteria, that is it a solution up to that tolerance or not? Okay, so I'm going to discuss about this after I just write certain steps. Okay, so I'll be going to discuss this, but we try to check is it a solution or not. If it is not a solution, then we try to see where our solution lies. Once it is not a solution up to the accuracy we wanted, then we try to see either I have to move A or I have to move B. So what is the condition I'm going to check? If function value at B times function value of P is less than 0, it means solution lies between B and P. So I have to move A. Otherwise means solution lies between A and P. Okay. So I have to move B. Okay. So this is the condition that will make either A at a position P or B at a position P, a central position. Some variable either A or B have to come at the central position. Okay. So this is the condition that will tell, okay, you have to follow this step. Okay. Once we're doing in the last lecture, we try to find the first central point of this equation, which is x minus cos x equals to 0 on the unit interval, and the tolerance we wanted 10 to the power minus 3. The first midpoint was 0.5, and the function value at central point was minus 0.3776. So it is not the solution up to the accuracy we wanted, which is 10 to the power minus 3. Okay, so the next thing is we go towards finding a second midpoint. Okay, a second midpoint was determined after this step number 3. So the solution lies between 0 and 1. At 0 we have a negative sign, at 1 we have a positive sign, at central point we got a negative sign. Okay, it was a P1. So we say, okay, solution lies over there. Okay, so, and it is not a solution up to the given accuracy. So we find a central point of now this subinterval. A has been moved to this position, and we find a central point. Central was our point at 0.75. So we find a central point which is 0.75. We try to check, is it a solution? If it is a solution, then obviously we need to stop. If it is not a solution, then we need to decide a subinterval where the solution lies. So this is the picture where we have an updated value of A as 0.5, we have an updated value of B as 1, and we have a second midpoint which is 0.75. So we negative sign here, positive sign here, and at a 0.75, if you calculate, we got a positive sign. Okay, if you calculate it, the sign is a positive sign. So if P2 is not a solution up to the given accuracy, we have to decide which variable has to move. So we again go to this condition and check if f of b and f of p is less than 0. Let's see over here. F of b and f of p, what are the signs? It is not less than 0. So we have to move what? B, because it's an else condition. Okay, so we move b from this point to this one. So now the updated subinterval is 0.5, which is A, and B is 0.75. We again find a subinterval, a midpoint, which is 0.625. So we again check, do a central point. We check, is it a solution? If it is a solution, we'll stop. If it is not a solution, we'll see in which subinterval the solution lies. So these 3 steps we are keep repeating. Okay, we just keep repeating these 3 steps. Okay, so it means we have to put these 3 steps in a in a what? In some, so we keep repeating these conditions. So we have to put, I'm talking in a programming sense, we have to put this into a loop. We have to put in, okay. So because the value of A is changing, the value of B is changing, okay. So the value of P is changing. So and they just trying to go as near to the solution as the accuracy we want, okay. So but generally speaking, these three conditions are the ones that we keep repeating in every iteration, okay. So if I just run these three steps one time, so we have one iteration. If I just find the two times, so it is, we got two iterations. And in the example that we did in the last lecture, if you see on your slide, okay, so we got uh, 10 iterations actually to get to the accuracy we want, okay. So how many times these calculations are going to be repeated will be called the iteration, okay. So okay, we have decided that we have to put into a loop. Now there are two types of loops. Anyone? For and while, and usually they're called conditional or counting loop. Okay, so we got two things. Either we have a counting loops or we have a conditional loop. Okay, so in this scenario, what do you suggest? Either we need a counting loop or we need a conditional loop. Conditional loop. And why conditional loop? Very right. Because at step 2, there is a condition that we need to be fulfilled. If that condition fulfilled, we got a solution. So we have a certain condition in this actually algorithm that needs to be fulfilled. So it means we need to use a conditional loop. Okay, and you know the conditional loop is the while loop. Okay, the while loop is the one which is the conditional. So we'll be focusing on trying to use the conditional loop onto these number of steps, but we have to discuss some more about that condition at which we need to stop. So what would be the condition at which we'll say, okay, we got a solution up to this accuracy. Okay, so now I'm going to discuss about the step number 2, which is P a solution up to the given tolerance or not? How to check that? Okay, so in other words, when to stop? Okay, so I'm particularly talking about the bisection method, but the findings that we're going to do from this discussion will be applicable on all the methods that we're going to learn. Okay, that when to stop, when we have to stop. Okay, so in other words, this is also called it's also called stopping criteria. Okay, so when we have to stop, what is the stopping criteria? So let's discuss that once we find a first midpoint, then the second midpoint, nth midpoint, because the sequence bisection method will be an infinite sequence, but we cannot handle the infinite terms. We actually do not require so many infinite terms. We have to stop it somewhere. So we need a finite many terms actually. So at which I need to stop? Okay, what is the point where actually I need to stop? Okay, so let's say Pi is a point in the sequence where uh, we have a solution up to 10 is power minus n. Okay, up to the tolerance we need to, up to the accuracy we wanted to achieve. Okay, so let's say in this sequence there is a point pi where we got this condition. So how I'm going to mathematically write that? So I'm going to write this condition in a mathematical way. It will be a function. When I will plug that pi into the function, okay, the answer will be near to 10 raised power minus 10. Okay, and a more clear way to write this is when I plug a function value, so it is less than 10 raised power minus 10. Okay, I just plug an absolute sign over here. I'll try to discuss this why I'm going to write the absolute sign, but this is actually the condition at which we need to stop. So for example, if there is a point, let's take an example. Let's say we need an accuracy of 10 raised power minus 2. Okay, this is the accuracy we wanted to achieve, and in the example, probably the example we're doing, the x minus cos x, you can see the table over there. Okay, so there is a point, if you see a point which is okay, we got a p6. Okay, so if you see a p6, it is 0.7344. Okay, so when you plug the p6 into a function, the answer is minus 0.0078. Okay, what is 10 raised power minus 2? So you need an accuracy in which when you plug into the function, it should be near to this value. Okay, so if you see this number, this particular number, this value, this function value, so we got a solution up to the 2 decimals. It is a 0. This number is 0 up to the 2 decimals. Okay, so what is a number that is less than this number? If I ask you, just write any number that is less than this number, it will be 0.00 something, whatever that will be, but that will be something 0.00. Okay, let's say 9. Okay, so 9, that will be a smaller number. So if you need an accuracy of 10 raised power minus 2, it means you need a number, you need a point in that sequence. When you plug into the equation, you got an answer that will look 0 up to 2 decimal places. Okay, so if you see a p6, you see a function up to 2 decimal places at 0, 0. Then you see a negative sign over here. So that is a perfect actually example to tell the why we use an absolute sign. If you're just seeing a solution up to 2 decimal places, and in a way that when you plug into the function, so up to 2 decimal places we got a 0. Okay, we got a 0. So the sign does not matter. Either function is, the value is positive or negative up to 2 decimal places. It is same as writing negative 0 or a positive 0. A negative 0 or a positive 0 means nothing. Okay, it is a 0 up to the so that's why the sign of the function does not matter to decide either we got a solution up to certain decimal or not. It will just an indicator that the solution lies in which particular subinterval. Okay, but if you check this particular example now, the absolute value is less than 10 raised power minus 2. So it means if we just trying the bisection method on this example, at the 6th iteration, I got a point where the function value when I plug into the equation is less than 10 raised power minus 2 up to the accuracy I want. Okay, so in other words, it is a 0 up to the 2 decimal places. Up to the 2 decimal places, it's 0, and the absolute sign is the reason that up to those decimal places the sign will not matter because it will be 0. It will be considered as 0 because it is considered as solution up to 2 decimal places. Okay, so or up to, you can write 10 raised power minus 2. Okay, so it means what you can write P6, which is 0.7344, is a solution. Obviously, it is an approximate solution. Okay, of x minus cos x equals to 0 up to 10 raised power minus 2. So that's how you conclude the answer. Okay. So this is the, generally speaking, this is the, so I'm going to drop now this particular portion, I don't need it. So this is the condition that we have. So at which pi you have to stop? At a point where the function value will become in absolute terms less than the required tolerance. If it is less than that tolerance, we need to stop there. Okay. So there are other criteria too, when to stop. We will be discussing in um, uh, the later on topics. Okay, but at this point we'll just be carrying with this stopping criteria. Okay, so now I'm going to update the step number 2, because I know that we got a solution up to 10 to the power minus n at which stage. Okay. Okay, so now I'll just try to formalize the step number 2. Okay. Okay, while formalizing a step number 2, uh, let's try to start from actually the inputs that we required once we're trying. So let's understand that we're trying to implement onto the computer system. Okay, and we're trying to develop a pseudocode. A pseudocode is one step after the algorithm. Okay, so what are the inputs? What are the inputs? So we are actually developing the pseudocode of bisection method. Okay, what are the inputs? Okay, so we got function that we need to approximate. So whenever the user will come, we'll say, okay, just give me the function equation you wanted to approximate. Okay, give me the interval where you want to find a solution. Okay, and the accuracy, right? We call it as a tolerance. Give me a tolerance you want to achieve. Give me an accuracy you want to achieve in this question. Okay, so so we have these inputs. Let's talk about the process. So what is the step number 1? Step number 1 is find a central point. Okay, find a central point of this. Uh, you can use parentheses to make sure that there is no mistake. So once we find a midpoint, we'll check. So now I'm going to formalize that step number 2. If uh, function at this point in absolute terms, okay, is less than tolerance, okay, at this midpoint I got a solution that matches my accuracy, okay, then do what? Then stop. Okay, stop the process and display. Display what? Exactly. What is the output? We got a solution. P is a solution up to the given tolerance. Okay, just display it. We got a solution. Okay. Okay. If this is not the case, that the point we just find it is not a value up to the given tolerance, then we have an else. Okay, then we go to step number 3. Okay, which is, so we got two ifs. Let's do it. If f of b times f of p is less than 0, move a, else move b. Okay, let's write a word end just to understand that the end of the statement. Okay, so I'm just writing over here end, and this end is actually connected with this if. Okay, and let me write another end. This end is connected with this if. Okay, so let's now try to see what is happening. So we hopefully every one of you understand the process till now. It's an easy one, just to find a central point, and we have to decide which subinterval we need to go. Okay, so we got a problem. We see, okay, we find a midpoint. Is that, if that midpoint is a solution, we say, okay, stop the process, we got a solution. If that is not the solution, then we try to find in which subinterval the solution lies. So this process will give, just rearrange the values of a and b, and then we'll come again to point where we do the um, half. Okay, again check if that half is a solution. If that is a solution, we'll stop. Otherwise, we'll keep continue finding the solution. By the way, this step number 3 is called a root bracketing. You're bracketing your root. You're trying to find where the solution is. Okay, trying to find in which subinterval the solution lies. Okay, this is called a root bracketing. You bracket your root. Okay, so now, as we just discussed, I just circled these steps. I just rewrite those steps in by just explaining more about the step number 2. We need to put this process into uh, in a loop, and we have decided that the wise way, or out of the options available, the condition loop is a good loop to go with, because there is a certain condition that need to be fulfilled. That condition fulfilled, we stop the process. If that condition does not satisfy it, then we keep trying to find a solution. Okay, so now I'm going to write a loop actually, and I'm going to, so the inputs are same. I'm going to write the process. I'm going to write the process because I need to plug in the loop. Okay, so any one of you, which condition we need to check? This one. Okay, so whenever I actually write while, it's same as if, but a repeated if. Okay, while is a repeated if. So is this a condition that we need to check repeatedly? Is this the one? Okay, so I'm going to write over there while. So just understand, rather than this if, I'm going to write a while. Okay, absolute value of a function, okay, is, I'm not going to write the sign over here, we'll decide it later on. So if this function value is what will decide that. Okay, so you have learned about the languages. You must have done some of the courses on probably the Python or some other language. Okay, so you understand that if the certain loop satisfied, for example, in terms of a while loop, if that condition satisfy, then you need to run certain set of statements. If that condition satisfy, then you need to run certain set of statements. If that condition in the loop does not satisfy, you get out of the loop. Okay, so when my loop will, the condition of the loop will not satisfy, I will come at this position. Okay, so I have to come at this position. What is the point? What is the condition when this loop will not have to uh, run a certain steps? Whenever I find a solution. Okay, whenever I find a solution, I don't have to find a solution further, obviously. Okay, so out of the two conditions of options, if f of p is absolute terms is less than tolerance or otherwise means greater than equals to tolerance, otherwise means that. Okay, so which sign I'm going to plug over there? Greater than or less than? Because you're right, very right, it's greater than or. If that point is not a solution, then I have to look for the solution. Otherwise, I just display that we got a solution. So I can just write over here, display P is a solution. So if that condition will not fulfill, it means it is less than tolerance. If it is less than tolerance, it will come out over here and it will display I got a solution up to the tolerance you want. Okay. So what are the actually working that I have to write over here? So that's why I just write this condition first, and then I have to do, or first let's do this. If f of b times f of p less than 0, move a, else move b. This is the end of this statement. Okay. Uh, now where is we doing the half of the interval? We have to do inside the loop. Okay, because this statement initially was written outside the loop. Okay, but we have to keep doing the half of the interval. Okay, so for example, in the first run, I'm not putting that value inside the loop. I'll write over here. So the first time the loop, the process will understand what is the value of p. Okay, but once it is running, for example, that p is not a solution, so it will find where the solution will lie. So it will change the value of a, it will maybe change the value of b. Okay, then we need to do the half again. Okay, we need to do the half again, but this point lies outside the loop, so this statement is not going to rerun again. Okay, this is outside the loop. This is the set of statements that we need. So I'm just right over here, p is equals to a plus b divided by 2. Okay, this is just the first time. By the way, you can to avoid this, you can use a do while loop. Okay, that is, do the working first, then check the condition. Okay, that is a do while loop. Okay, so in a simple while loop, you just check the conditions, and I am just trying to be naturally trying to develop an algorithm or a pseudocode out of the observations we can have. Okay, so and once this condition will not fulfill, it will display p is a solution. And what is this, by the way? This is the output. This is the output. Okay, we got an output p as a solution. We want a solution up to certain accuracy, and this will be the output. Okay, so if you see, just connect this input. So if I just write the inputs over here, which is function a, b, and tolerance, this set of statements will is a pseudocode actually, very much near to the code that we're going to develop on the MATLAB for the bisection method. It is a bisection method. Okay, that will, now you can just keep improvising it. That maybe if you ask me that, for example, if a user enter a value of a and b where the solution does not lie, if f of a, f of b is not less than 0, for example, so you can just try to put a check over there that is f of a, f of b is less than 0. If f of a, f of b is less than 0, you will proceed with your code. Otherwise, we just message the user that the solution probably does not lie between A and B. And hopefully, you know why I use the word probably, because if f of a f of b is greater than 0, then you might have a solution. It's not surety, but you might have a solution. Okay, so you can just improvise this pseudocode as you just try to develop. So in the probably in the next week, we will be implementing this pseudocode into the MATLAB. Once we go to the basics of the MATLAB, we will be that will be our target. Okay, so uh, uh, please write this particular code. We will be needing it again. Okay. 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 There is one more thing which just give us the estimate of how many iterations actually you need to find a solution up to certain accuracy using a bisection method. It's a just small result, small result. So I'll just write over here. Um, um, so so let's wrap up this lecture. Okay. So in this lecture, actually, just summarized way, we are able to develop a pseudocode of the bisection method that we are going to implement on the MATLAB. Okay, and in the coming up lecture, hopefully, we'll continue with the more findings of the solution of the one variable. Thank you so much.